Hi, welcome to TechTime with Kayla. Today we're in Federal Signal's in-house photometry lab, where Bob, our principal mechanical engineer, is going to talk to us about the importance of light in signaling. Bob, can you tell us a little bit about where we are today?
Sure. This is the photometry lab at Federal Signal Corporation. To the left side of us, there's an area where we do optical experiments on an optical table, and we also do total light output measurements within a lumisphere and integrating sphere. But the majority of the work that we do is done here. On this side of the lab, we have a goniometer and a far field detector. And here we could do far field measurements of the light intensity or effective intensity measurements of any signaling devices that we're producing.
Can we talk about the different types of light sources and the benefits of each one?
Sure, absolutely. What we have arrayed up here are the three most common light sources that have been used in emergency warning lights. The first one is an incandescent lamp, and that goes back to Thomas Edison's time, where we have an incandescent filament that's basically producing the light. Next, we have a strobe light or a gaseous discharge lamp, and then the last one is an LED source, which is the most prevalent light source today. Incandescent lights, very simple electrical system to drive them. They have moderate life, typically around 2,000 hours or so. They're very susceptible to impact and vibration damage, okay? The strobe light required a much more complex electrical system to drive it. It has typical lives around 2,500 to 3,000 hours. One of the things that is unique about a strobe light is it produces a very, very high peak intensity, but it's only for a very, very short duration, a little bit less than a millisecond. The LED light, in contrast, produces a fairly intense beam, nowhere near as intense as the strobe light, but its on and off times are almost instantaneous, so it creates very close to a true square wave. So that allows you to make adjustments in your flash patterns, and basically, by adjusting the flash pattern, improve the conspicuity of the device itself. It does require some electrical circuitry, but it's nowhere near as complex as the circuitry that's used in a strobe light. And it's also more robust. It's probably typical lifetimes for LEDs are around 50,000 hours, and they're pretty impervious to impact and vibration damage.
Are any of these lights measured differently, or are they all measured the same?
Nowadays, they're all measured the same. In fact, why don't we take a walk down to the end of the tunnel and I can explain to you how we're actually doing the light measurement here. It all starts with the photodetector that's 60 feet down this tunnel.
Perfect.
Okay, the measurement of light begins at this end of the tunnel with our detector tree. The detector tree actually has a couple of detectors and an alignment laser. The alignment laser fires back towards the device that's under test and allows us to align its position with the detectors that are on the tree. This lower visible light detector has an electronic chip inside of it that basically converts light energy to an electrical current, which gets sent back to the console where it's converted into candelas. There's also a filter on the front end of this that adjusts the light levels to what our human eye sees, so that the numbers that we're getting out of this cell is the exact same as we would get them, what our eye would physically see. So why don't we go down to the other end and we'll take a look at the goniometer that controls the angular placement of the device. And on this end of the tunnel we have a goniometer, and this goniometer's whole purpose is to actually rotate the unit that's under test to the left, very accurately to the left and to the right, or up and down. And the reason that we need that capability is most of the standards that are written have prescribed locations with angular offsets that we have to meet specific light output numbers for. So we need to actually, when we test a light like this, we'll do an HV peak intensity measurement, and then we'll check the intensity at various angular offsets from that.
Can this unit measure both peak and effective candela?
Yes, it can. But the one thing that you need to recall or need to think about with effective intensity is a way of taking the light measurements here and accommodating how the human eye sees it to try and make a comparison between a steady burning light and a flashing light. So what the effective intensity really means is it's the equivalent steady burning brightness that has the same brightness as this particular flashing light. So it takes into account not only peak intensity, but also the waveform of the flash and all those other things.
So once you have your light output value, how do you determine the beacon effectiveness range?
To calculate the beacon effectiveness range, you need to know what the atmospheric conditions are like. Is it cloudy? Is it a brightly lit day? Is it overcast? Because all of those elements enter into doing the calculation. You need to know the peak intensity of your device. You also need to know what the luminance of the background is. In other words, if it's being backlit by a very bright cloudless sky, the effectiveness of the intensity is going to be much less because the contrast between the two is so much smaller. If the background is a dark area, like say foliage in a forest or something like that, the visual range is going to be higher because the contrast difference between the background and the signal is so much greater.
Bob, thank you so much for your time today. This has been very enlightening. For additional information on our visual signals, visit our website at signaling.fedsig.com.